So before starting the application of derivatives, I want to give you a brief overview about the differentiation, brief introduction. I hope you have studied that in your 11th and 12th. If you haven't, you can watch this in 2x and we can quickly revise the concepts of differentiation. Okay, so not that difficult, we'll go fast. So differentiation are of two types. So one is ordinary, where I have only one variable, right? One independent variable. Y is a function of x, which is an independent variable. X can take in any value within its domain. Okay, so if I differentiate it, that will be f dash of x equals to y dash, right? So this is how a ordinary differential equation looks like. Now next is partial differentiation. What do you mean by partial? Partial means not complete, right? Just half baked. So what does that mean? This means I have a like a function, okay, z, which is a function of two variables. Okay, I have a value z, which is a function of two variables x and y. X and y are independent variables. They can take in any variables they like. Okay, they are not dependent with each other. They are independent. X and y are independent of each other. Okay, so they can take in any value they like. Now what I will do, I will differentiate. But the confusion lies with what, with respect to what I will differentiate. So I can differentiate with respect to x, I can differentiate with respect to y. But what about the other independent variable? What will happen to the other independent variable? So what will happen is that if I differentiate with respect to x, I will assume the other independent variable as constant and I will find my f of x. The notations are written over here. F of x, we can write that this means that I have partially differentiated with respect to x, or z of x. This also means the same thing. Or f of y, this means I have partially differentiated with respect to y and z of y. So basically we will study about this partial later on. Currently we study about this ordinary differentiation only. Okay, so I just wanted to give you a brief overview of what we'll study. So basically let's start with the question. Okay, let's crack a question. So we have to find the differentiation of the following functions. Okay, so I hope you remember the formula. If you don't, you have to quickly put those things in short notes. Okay, put the formulas in short notes and try to go through those every day, right? Every day, 5 minutes at least give it 5 minutes and go through those every day. Okay, so now, right, this is 1. Okay, we'll find the dy dx of the 1. So dy dx my fan is making some weird noises. So what is differentiation of cos x? Cosec x. So how you remember? You remember the sec x. So what is the differentiation of sec x? Sec x is sec x tan x. Cosec x is one negative sign gets added, and obviously it can't be tan x, it has to be cot x instead of tan x. So that's how I remember, right, about the differentiation of cos x. So it will be minus cosec x cot x. Okay, then minus sec inverse of x. Now this is difficult, right? Minus sec, differentiation of sec inverse of x is difficult. Okay, so I will write so what you can do, we can apply the chain rule, right? We can apply the chain rule. Okay, so if you remember differentiation of sec inverse of x, that is very good. If you don't, then you have to again go back to the formulas, right? It was 1 upon mod x into under root of x square plus 1. Okay, it was something like that. So yeah, here I have a product, right? I have a product. All this I will explain. This is we are using the chain rule. I will explain in the next slides, but if you know, that's great, right? So plus this is minus sec inverse of x into d dx of cot x. Now what is the differentiation of cot x? And this is, I will put this in bracket, into sec inverse of x. Okay, so this will be equals to so dy upon dx will be equals to, so what is this? Cosec x into cot x. So it is 1 by sine into like okay, let me keep it like this only, and this, right? So what is this? This is cosec square x minus cosec square x, right? So if you remember correctly, what is the differentiation of tan x? Tan x is plus sec square x. This will be minus cosec square x, just the opposite of tan x, right? So this will become plus sec inverse x into and this is minus cot of x divided by mod of x under root x square plus 1. Okay, so basically this is the answer. This is the answer. This is the answer to this question, right? Answer. Okay, I can't further simplify this. Okay, I can't further simplify this. So let's solve the second one. These are difficult, obviously. Okay, if you are not able to do this, don't worry. Okay, just I want to, why I am taking this question, just to show you that you have to try to mug up the formulas. Okay, for differentiation you have to mug up the formulas. There are no other options. Okay, so this is a bit easier one. So you have this function x raised to power minus up, so this will be minus 1 by 2 into x raised to power minus 3 by 2 plus again I will apply the chain rule, 2x into 1 minus x plus x square into minus 1 plus 1 by under root 1 minus x square, right? So now I can simplify this a bit. Dy dx will be simply, so this is now this, right? What is this? This is minus x square, this is minus 2x square, so overall this becomes minus 3x square. So minus 1 by 2 x raised to power minus 3 by 2 minus 3x square plus 2x plus 1 minus x square. Okay, so yeah, this is the solution, right? Okay, so what I have been applying, so I am applying some rule, right? So this multiplication I am applying some rule. Okay, if you don't know already. Okay, here also I applied some like simplification. Okay, I directly didn't find the differentiation of these two products. I individually found the differentiation, right? So what is that rule called? That rule is called chain rule. With the example of this we'll understand. Okay, so we have been given this function y equals to 3u square plus 2 and u equals to 2x plus 1. So this u is a function of x. Okay, this y is not directly a function of x, but what I am interested in is the dy upon dx. So differentiation of y with respect to x, that is what I am interested in. So what I will write y as a function of u. Okay, and then my u as a function of sorry, not u as a function of x. Okay, so basically my y is a function of u, right? And u is a function of x, so I can write it like this. This is like a composite function. This is like a composite function, right? Composite function. Okay, so what you can do one thing, substitution. So here u is equals to 2x plus 1, you can directly substitute and then directly find dy upon dx. So this is the method 1. So method 1 is substitution. So basically what you do y is equals to 3 into 2x plus 1 whole square plus 2. Okay, 3 into 4x square plus 4x plus 1 plus 2. Okay, y equals to 12x square plus 12x plus 3 plus 2. So this is equals to 12x square plus 12x plus 5. Okay, so what is my dy upon dx? My dy upon dx will be 24x plus 12. Okay, 24x plus 12. So if I take common 12, this will be 2x plus 1. Okay, so this will be my dy upon dx. So now let's solve using the chain rule, right? So this is substitution. Let's solve using the chain rule. So how do you solve using the chain rule? So basically we have to find dy upon dx. What we can do, we can write this dy upon du into du upon dx. We can individually find the derivatives. Okay, so what is dy upon du? So dy upon du is simply this, right? So dy upon du will be 6u. And what is du upon dx? Du upon dx is simply 2. Okay, how, you know, right? So this is 12u, so I can write 12 into what is u? U is 2x plus 1. Okay, and exactly that is what we got, right? So it took us 2 lines here, or not even 2 lines, 1 line, because this was the derivation, and here it took us so many lines, right? So that is the advantage of chain rule, right? That is the advantage of chain rule. Even if it is not a function of x, I can easily find out the differentiation with respect to x by finding the differentiation with respect to u and then multiply with du upon dx. So yeah, that is the advantage. So this is the generalized chain rule. If I have multiple functions, right? I have u, then u is a function of v, then v is a function of y, y is a function of z, okay, and finally t is a function of x. So I can use the generalized chain rule and multiply each of these derivatives to finally find out dy upon dx, because everything else will get simply cancelled, right? Everything else will get cancelled except dy and dx. Okay, except dy and dx, everything else will get cancelled. Okay, so now you have to find dy upon dx. Now we have to find like dy upon dx of this, right? Now we'll apply the chain rule. Sorry, I was thinking in my mind I was thinking something else. Sorry. So how to find the derivative of this? So again we'll apply the chain rule, right? How will you apply the chain rule? So what you can do, okay, like slowly, when with practice we'll do this directly instead of substituting. Okay, but here I will substitute, right? I will substitute. So what I will do, I will assume a function new u as cot inverse of under root x. Okay, I will do the most lowest hierarchy. So what I will do, I will take a function v which is equals to under root v. I will take a function u which is equals to cot inverse of v, right? Because v is under root u. V is under root x, and obviously my final function y is under root of u. Okay, so what I will do, I have to find out dy upon dx, right? So I can break it down, dy upon du into du upon dv into dv upon dx. Okay, so basically what will happen over here, that my dy upon dx, so this is dy upon du. So if I have dy upon du, so this will be simply 1 by 2 by under root u, right? So u comes in the denominator, u raised to power minus 3 by 2, minus 1 by 2. Now this, right, what is this? This is du upon dv. So if this is du upon dv, so this will be this again, this will be, sorry, du upon dv is this, sorry, du upon dv is this. So what is my cot inverse of x? Okay, you have to find the differentiation of cot inverse of x. So if you like remember correctly, it is minus 1 by under root x square, right? Because tan inverse of x plus cot inverse of x is pi by 2. Okay, hence like you can just recall that it will be the opposite sign. It will be the opposite sign, right? So hence, sorry, I was doing wrong here. This will be minus of 1 by x square, but here instead of x we have v, right? Instead of x we have v, so this will be v square. This will be v square into the other one, right? This one. Now what is the differentiation of dv upon dx? It will be simply 1 by 2 into 1 by 2 under root x, right? 1 by 2 under root x. So simply, what is under root u? What is under root u? Under root u is simply y itself. Yeah, you can write it as y, no worries. Or yeah, let's not write it as y. What we'll do, u is what? Cot inverse of v, and v is what? Under root x. So under root u will be cot inverse of under root of x. Okay, into minus 1 plus v square. So v is basically under root x, so this will be 1 plus x square into, obviously we have under root of x. Okay, so this will be my final answer, right? This will be my final answer to this question. Okay, so what I want you to do is to solve this in a single line. How will when we'll solve again this question, we'll understand. So here, how you solve. So first thing what you do is go from outside, then go inside, right? Go from outside, then slowly go inside. So first I have under root of cot inverse of x. So first I will differentiate under root of some function. Okay, what is the differentiation of under root of anything, right? What is the differentiation of that? So first I will write dy upon dx, and then I will write what is the differentiation of the outside function, under root function. It is simply whatever is inside, okay, you divide it, because the power will reduce by 1. So currently the power is half. If it reduces by 1, it will be minus half. So it will come in denominator. This under root thing will come in denominator with whatever trash is inside, and obviously I have to multiply by the power itself, which power was there. Currently half, so I have to multiply half also. So half, and this will come to the denominator, right? Cot inverse of x. Okay, now next, then I have to go inside, right? Then if I go inside, I have to differentiate cot inverse. Okay, cot inverse of under root x, but I will only care about cot inverse right now. What is the differentiation of cot inverse? The differentiation of cot inverse is minus 1 upon whatever is inside the cot inverse, square of that. Okay, square of that. So it will be simply minus of 1 plus under root of x into whole square, right? Whatever is inside that cot inverse function. Okay, then I will finally go inside to this under root x. So what is the differentiation of under root x? Obviously everything is coming in multiplication, that we know, from chain rule, right? Okay, what is the differentiation of under root x? Again the same thing. The differentiation of under root x will be 1 by 2. Let me reduce. Into under root x, right? 1 by 2 into under root of x. Okay, that is the differentiation of this function, right? That is the differentiation of this function. So this will be the simply answer to this question. So like this is how you solve. So you first go outside, then slowly go inside. This is how you use a chain rule, right? And when multiple functions are there, this is a composite function. So when multiple functions are here, this is how you use the chain rule. Okay, so let's use it without any substitution. Okay, I used substitution here, I won't use for this, right? So what will be the differentiation of this? So my function is this, right? Function is this. So my function is, I can rewrite this like this, f of ax plus b whole inverse. Okay, so now from outside I will go inside. So I need to find dy upon dx. Okay, so what is outside? Outside is a power raised to power minus 1. So obviously what is the differentiation of these type of functions? This will be, the power will come in front and I will reduce the power by 1. Okay, and then I will go inside. So if I go inside this power, you will say, sir, this is inside. No, this function is also there, right? So first I have to differentiate this function. So what is the differentiation of this function? The differentiation of this function is f of ax plus b, f dash of ax plus b. I don't know because function hasn't been given to me. Okay, so I will simply write it as it is. what does this represent? This represents the differentiation of the function f of ax plus b. Now I will go further inside. Further inside is this ax plus b. So what is the differentiation of ax plus b? The differentiation of ax plus b will be a only, right? Will be a only. Okay, so this will be f dash of ax plus b divided by f of ax plus b whole square into minus a. Okay, into minus a. So this will be the answer to this question. This will be my dy upon dx. Or how you could have done, you solve it for yourself. You use the method of substitution. Okay, so what do? You assume that like v is some function ax plus b, then u is f of v, and my y is u raised to power minus 1 or 1 by u. Okay, and you can apply the chain rule here, right? You can apply the chain rule here, your wish. Okay, so let's now solve another type of question where I have to solve differentiation using logarithm. Okay, logarithm. So basically these type of functions, right, when I have a power, okay, as a function of x, is tedious to solve. So first what we do, we take the log, okay, then we write it in terms of multiplication, then it becomes, we'll use the chain rule, and then it becomes much easier to find the differentiation. So what we'll do, we'll take log on both sides, natural logarithm. So this power will come in front with the property of logs. So this will be ln of f of x, and now I'll differentiate it. So what is the differentiation of ln of x? 1 by x. But here I have chain rule, right? If I differentiate this will be whatever is inside, it will come in reciprocal 1 by y. Also I have to differentiate the inside function as well, that is dy upon dx. So if I differentiate on both sides, this will be dy upon dx into 1 by y into dy upon dx equals to, now again I will apply the chain rule over here, right? Apply the chain rule over here. This will be zetas of x into ln of f of x, okay, plus g of x upon f of x into f dash of x, right? Because obviously I have a inside function as well. Right? So I have to, obviously whatever is inside this ln of x, divide that, then multiply with the differentiation of that inside function. Okay, so what will be my finally answer of dy upon dx? Dy upon dx equals to f dash of x into g of x by f of x plus g dash of x ln f of x. Okay, so this is my answer. So y I can write as f of x also. So this y is equal this, right? This y is this, so I can replace this y with, so this will still remain just like exponential. If you remember, just like exponentials, okay, this will still remain f of x g of x, right? So just like you should remember, a raised to power x into ln of a, just the same thing. E raised to power x is still here, okay, this f of x raised to power g of x is still here, and this extra term is present, right? Extra term is present. So let's solve our question. From there we will understand this better. So here we have been given dy upon dx into log of x, right? Log of x. Let's name this as log of a x. So what we can do, we have to find the differentiation, right? So first we'll take the log on both sides. This will be ln of y into tan of x into ln of log of x. Okay, now we differentiate on both sides. So this will be 1 by y into dy upon dx. Now I will apply the chain rule. So this will be sec square x log of a x. Now how to differentiate this, right? So this how I can write this, I can write like this: ln of x divided by ln of a, property of logarithms. I hope you understand this. So tan x will still remain outside, and I have to differentiate this, right? Differentiate this. So obviously this ln a is constant. This ln a I can pop in front, right? Ln I can pop in front. Okay, and what will it get multiplied to? This will get multiplied with like this. I have to differentiate with respect to ln of x. So this will be 1 by x. Okay, yeah, that is it. So what is y? Y is log of ax raised to power tan x, right? Log of ax raised to power tan x. Now what is this? This is ln of log of ax sec square x into ln of log of ax. Okay, plus this, right? This is basically equals to tan x by x ln of a. Okay, so yeah, this will be my answer to this question. Okay, this will be my simple answer to this question. Okay, so yeah, let's solve another differentiation topic, that is differentiation of parametric functions. So if I have parametric functions, what do you mean by that? Now my x is a function of r and t, my y is a function of r and t, both these are function of r and t. Okay, but what I have to find now, this r is constant, I have to find dy upon dx. So both are functions of some other two variables, but what am I interested in? Okay, I am interested in dy upon dx. Okay, so here what is the important point? X comma y both are functions of parameter t, right? Parameter t. But what am I interested in? I'm interested in dy upon dx because I'm in love with this. Okay, sometimes we get obsessed with someone, right? So that is exactly what is happening. I'm obsessed with dy upon dx. So how to find that? So here I will write few things, that if my y is a function of t and my x is a function of t. Okay, so what I will do, what I can do, I have to find dy upon dx, right? I have to find dy upon dx. I can simply do this, right? Dy upon dt upon dx upon dt. So dt gets cancelled and I have dy upon dx. So I can write this as f dash of okay, this is not ff t because this both of them will be same only. I will write this as g of t, right? G of t, to differentiate these two things. So this will be f dash of t and this will be g dash of t. Okay, f dash of t and g dash of t. Okay, rather simple. So this is how you solve this type of question, or yeah, you have to remember this, right? You have to remember this. So this you can put it in short notes, or like this pretty easy to understand. I don't think there is much into this. So yeah, this is the case. So let's come to our example, right? r is constant, they have told us that r is constant. If it was a variable of like 2, if it was function of 2 variables, obviously it would be difficult. We have to use partial derivatives, and that has another formula. We'll do that later on. So we have to find dy upon dx, right? So first I will find dy upon dt, which is r into cos t upon dy upon dx, dx upon dt, which is r into minus sin t, where r is obviously constant. So this will be minus cos t upon sin t. What is it? It is cot of t, right? Cot of t minus cot of t. Okay, so this will be my answer to this question. Okay, so there is another topic left, that is the differentiation of implicit function. Okay, after this we will study application of derivatives, that is AOD. So what is the differentiation of implicit functions? So here I can't break this, right? I can't write y equals to some function of x. I can't do that. Okay, I can separate this y. Okay, so how to solve this then? How to solve this? So what we can do, we can directly differentiate this. We can directly differentiate this on both sides. Okay, so up here we can actually do this thing that this x can go up here. Okay, and then I can take the under root, and yeah, that will be equals to my function, that is that I haven't thought about. So what I could have done is I could have done this, right? Oh, that will also be same only. What else I can do? X second multiply x square. If I multiply this, okay, that will also not work. Yeah, tan inverse of yeah, you can go with this. Okay, I will think about something else later. So now we differentiate with respect to x on both sides. So if I differentiate, what will happen? So basically this will be 2x, this will be 2y, and whatever is inside I have to differentiate. So here I differentiated x square with 2x, and what is inside x? What is the differentiation of x? It is 1. That's why I don't go further. Okay, so this is 2y into dy upon dx minus 0. So this, like my dy upon dx, in terms of y and x, I can write minus x upon y. Okay, minus x upon y. So this is my dy upon dx. Okay, so this is how you solve implicit functions. Okay, so now we'll start with applications of derivative, and please be attentive in this session because many questions come from this, right? Monotonicity, maxima, minima. Okay, so like very important. Okay, maximum, questions come from this, okay, topic, and most of them you will be able to solve with just basics. You don't need to remember anything, recall anything. You can solve with basics. Okay, so we'll start with application of derivative. Okay, so let's start with the first topic. So what is the first topic? First topic is derivative as rate measure. So the idea is these two are very similar to each other, not exactly equal. So I will say these two are very similar to each other. I think this will be single M. Okay, so these two are very similar to each other. What is like what do you mean by similarity? So here I have 2 points A and B, and the distance between them is, let's say, delta S. Okay, distance between these 2 points is delta S. Okay, so I have a particle x and that has traveled distance delta S, and in what time has it traveled? It has traveled in delta t time. Okay, time and distance. Now can you tell me about the speed? So there are 2 types of speed over here. One is the average speed and another was the instantaneous speed. What do you mean by average speed? Average speed means throughout this whole journey what was his average speed. How do we compute that? We compute that with total distance over total time. So this we have studied in physics. I won't like derive here obviously. Total distance upon total time which is equals to simple delta S upon delta T. Okay, delta S upon delta T. So this is my average speed. Okay, and this is also known as the rate measure. Now let's compute the instantaneous speed. At each point, what can be the speed at that particular point, right? At that particular point, how do we compute that? So basically copy this again. Now this will be instantaneous speed. This will be average. Instantaneous speed. So in this case, right, what will be my instantaneous speed? My instantaneous speed will be ds upon dt, right? My instantaneous speed will be ds upon dt. At that particular point, what is my speed? So it is ds upon dt. I hope you know the meaning of this derivative, right? It is the instantaneous at that particular instant. Okay, so like here also we will understand this better graphically. So here I am at x and I have moved distance like delta x, right? And also the y coordinate has moved distance delta y. So at each particular point, what will be my rate of change at each particular point? So each particular point, my rate of change will be simply, let's say here, right? What is my rate of change? This is tangent, right? Just hold on a second. Pen is not working. What is happening nowadays with this pen, man? I'm just tired of this. I need to buy a new pen. Oh no. Extremely sorry for the delay. So here, right, this is a tangent. So at this point, the rate change, right, instantaneous rate change, instantaneous rate of change is what? It is equal to simply dy upon dx, right? At this particular point, let's name this point as a. Okay, let's name this point as a at x equals to a, right? And what about the average rate of change? So overall, right, in this over range, what is my rate of change? So overall, I can say average rate of change is what? Delta y is delta y. I mean, sorry, yeah, change in y is delta y, and change in x is delta x. So delta y upon delta x. Now these two are very similar when these, right, this is smaller, this is smaller. Okay, this delta x is very small. These two are very similar. Okay, these two are very similar to each other. Okay, so yeah, we'll solve the questions from there. We'll understand this concept more in more deeper manner, right? So here I have been given, if the volume of a spherical balloon is increasing at the rate of 900 cubic centimeter per second. So it is increasing, the volume is expanding, right? Volume is expanding at the rate of 900 cubic per centimeter. So it is increasing. Like initially my sphere was like this, okay, then it become like this. Okay, and what is the rate at which it is increasing? Okay, it is increasing at the rate of what? 900 cubic centimeter per cube. So I can write this like this also, cubic centimeter per cube, cubic centimeter per second, sorry, cubic centimeter per second. Why is this the case? Like, what do you understand by, like, let's, in this case, right, units are very important for these type of questions. So cubic centimeter, that means this is the unit of volume, cubic, and per second. So per second it is increasing 900 cubic centimeter. So how can I write this, okay, in mathematical expression? So volume is increasing, so I will write here dV, okay, in the numerator, and as it is, this unit is in the numerator, and second, right, per second. So what will be this? This will be dt. So this, right, this also says the same thing. At what rate is my volume increasing per second? The units, I have to match the units, just take care of the units. So centimeter cube per second, so it is increasing at 900 centimeter cube per second. So this is how you decode the question, okay, this is how you decode the question. Now what is the question asking us? To find the rate of change of radius of the balloon at instant when radius is 15 centimeter. So at instant, right, it is talking about instantaneous, at that instant, instantaneous, okay, instantaneous. Maybe I would instantaneous. Okay, so yeah, these are the few things you have to keep in mind. So just hold on a second. So here, right, we have to talk about the rate of change of radius, okay. So for some, like, for some reason we have to find the radius, right, equation of radius with respect to volume. We have to find the relation of radius with respect to volume, then only we can solve further, because we have been given this one information, and from this information we have to find dr upon dt. So it's very important what you have to find, okay, and what you are given, okay. So how do we solve this question? So one thing I know, that what is the equation of volume of a sphere? The equation of volume of a sphere is 4 pi by 3 into r cube, right? This is the equation of volume. Now I have radius and volume over here. So if I, for some reason, I differentiate this with respect to time, and this right hand side also will be differentiated with respect to time, and I will have this dr by dt on the right hand side. How? I'll show you, right? So again, right, this is a parametric equation, okay. This like this is a parametric equation. As my v, okay, again this pen is not working sometimes. As my v is a function of time, and my r also is a function of time, right? V is a function of time and r also is a function of time. Both are functions of time, okay. So this is a parametric equation. I can differentiate with respect to time, okay, on both sides. So here what will happen? So if I do dv upon dt, okay, on the right, left hand side, this will be like constant will be outside only, and I will apply the chain rule again. So the differentiation of 3r cube will be, okay, sorry, I went to do here only, differentiation of r cube, just hold on a second. Yeah, differentiation of r cube will be 3r square, power comes in front and one power is like deducted, then obviously I will differentiate the inside function, that is r, which will be dr upon dt, which is not 1, it is also a function of time, so it will not be 1 in this case. So yeah, I got my desired quantity which I wanted to find out. So what is this? This is simply this, right, 900 centimeter per cube, and they have also asked in centimeters. So just be careful of the units. The units are same, so I won't do anything with them, right? So my what is the expression for dr by dt? The expression for dr by dt is simply 1 by 2 this 4 pi r square into dv upon dt. Now 1 by 4 pi r square. What is 1 by 4 pi r square? 1 by 4 pi r square. R square is 15 into 15. Square into dv upon dt, which is 900. Okay, now obviously 225 into 4 is 900, so that will be cancelled and it will be simply 1 by pi, okay, which is simply equals to 7 by 22. Okay, what is the value of 7 by 22? it will be something 0.33 something, 7 by 22, 0.31, 0.318, okay, or I can say 0.32, okay, and this is in centimeter per second, okay. So just be careful about that you have to take care of the units. It is very important for us to understand that units are very important in this lecture. So if they have given as meter per second, then I had to divide by 100, because how to convert centimeter to meters, you divide by 100, right? So that is how you solve this types of question, derivative as a rate measure. Let's go to the next question, and from there also we'll understand this better. So this question is bit typical. A man of height 1.8 meter moves away from a lamp post of height 3 meter. So I have a lamp post. Just let me draw along, right? It is very important, these type of question, right? When these type of question comes up, you have to draw along. So my lamp post is 3 meter and man of height of 1.8 is moving away. Okay, so I have this man of height of 1.8, right? So it will be something like this. .8 meters. Now what next? Then at a speed of 2 meters per second. So it is moving away at a speed of 2 meters per second. So let me first mark few points here, right? This is my distance x, okay, x distance, and this man is moving at a speed of 2 meters per second. That means my velocity, or dx upon dt, I hope you have studied it in physics, right? Dx upon dt, or velocity, rate of change of distance with respect to time, is 2 meter per second, okay. So yeah, we know the speed of the man. Now what next it is telling us? Find the speed at which the length of the shadow is increasing, okay, length of the shadow is increasing. So here I have a lamp, so lamp will illuminate, right? Illuminate the light. So what will happen? Where will the shadow fall? Where will the shadow fall? The shadow will fall somewhere around here, right? You just try to stand in front of the light, the shadow falls behind, or you go like this, the shadow is behind me, right? If you see, yeah, the shadows are behind me, some light is coming over here, the shadows are behind me, okay. If I walk like this, the shadows will be again behind me, right? Shadows will be again behind me, okay. So they are asking at what length the shadow is increasing. So here, where will the shadow fall? Shadow will fall around here, right? Shadow will be in front of us, okay. Now I don't know what is the length of the shadow. I don't know what is the length of the shadow, right? I don't know what is the length of the shadow. Okay, I will mark some arbitrary point, like this is A, B and C, okay, and this S, right? This S is the length of the shadow, this X is the distance from the lamp post and the man, okay. These are the few points you have to keep in mind. So at this particular point, I don't know, at B point, where my man is at B, I should also write increasing in meters per second. So when my man is at point B, the length of the shadow is this, the distance between the lamp post and the man is this, okay. Now if this further changes to delta x, okay, it increases delta x, then by how much my shadow will increase, how much length my shadow will increase. Shadow will be always, like, if lamp post is behind you, shadow will be in front of you. You try to stand in front of a lamp post and you try to do that, right? So this is a very good question. What we can do, okay, this is like a triangle question, right? So similar triangle question, so I can connect these point total, okay, from, let's name this as ABCD. So DC has been connected, okay, and again I will draw a parallel line with respect to x. So this distance, right, what will be this distance? This overall is 3 meters, okay, this overall distance is 3 meters, that is fine, okay, fine, that is fine. This overall distance is 3 meters. Now what else can I do? So I have a triangle of ACD, okay, and I have a triangle of what, this B, okay, this point I have to also mark. I have a triangle of EBC, okay, triangle of ECD and EBC. So now their angles are 90 degrees, okay. They have like this angle is also same for them, okay, this and this angle is also same for them, So hence what we can say, these triangles are similar, right? These triangles are similar because all the angles are same, because this angle is 90 degrees for both of them. Okay, both of them has 90 degrees angle. Okay, and this angle is common between them, so the other angle will also be same. I mean this angle, right? Why? Because the summation of all the angles of a triangle is 180 degrees. So this angle and this angle will also same. So angle similarity. So A, CD and EBC follow angle similarity. So what we can say is that this total distance, right? So the ratios will be same. So I can say AC upon this AD will be equals to this BC upon EB. Okay, so what is AC? AC is x plus s upon AD is 3, and my what is my this BC? BC is s upon EB, which is 1.8. Okay, so I'll go to the next page. Now if I go to the next page, what I will do, I will just divide this by, this is 3, right? So this will be 0.6. Yeah, 0.6 into x plus s equals to s. Okay, so this becomes 0.6 into x equals to 0.4 into s. So my s becomes 3 by 2 x. Okay, so my shadow is larger. Shadow will be larger. Why? Because the lamp post has greater height. If this lamp post has greater height, the shadow will be larger than this height of the man. Okay, so not height, the distance, right? Distance of the body. So now what I can do, we have found out the relation. So in this case, right, you have to find out the equation relation. You have to find out the relation between this x and s. Then only you will be able to find the rate of change. So they gave me information about this x and the distance, all these things, and then from here I found out those things. So now if I differentiate again, right, these s and x are parameters, right? So I can differentiate on both sides. ds upon dt equals to 3 by 2 into dx upon dt. So it is 3 by 2 into dx upon dt. Dx upon dt they have already given me, right? I've already written it over here. It is 2 meters per second. Okay, 2 meters per second. Let me bring this a bit. Yeah, 2 meters per second. So at the rate at which my shadow will be increasing is 3 meters per second. Very simple question to solve. Just you have to draw the diagram. In this case, right, you have to draw the diagram very clearly. Okay, let's go to another question. So for the ellipse, at what point does the ordinate decrease at the same rate as the abscissa increases? So they have given you the equation of ellipse, and they have told us to find that at what point the ordinate increases, the rate of increase in ordinate and the rate of decrease in abscissa. Okay, I've told you opposite. Rate of decrease in ordinate and rate of increase in abscissa are same. Okay, but what is ordinate and abscissa? So this, right, you have to put it in your short notes. If you remember, that is well and good. If you don't, you put it in your short notes. I also tend to forget these things. So what is ordinate? Ordinate is basically the y-axis. Okay, ordinate is basically the y-axis. Y-axis. And what is abscissa? Abscissa is basically the x-axis. Now how do you remember this? What you can do is you can say that, like, how do I start my graph? I start my graph with x-axis, right? So A is the starting alphabet. Okay, so I will start with x-axis, start my graph, and then whatever is remaining, ordinate will be y-axis only. So this, right, you have to put it in your short notes if you tend to forget these things. Okay, so like, how is my ellipse? Let me just draw a basic ellipse, and from there we'll understand this further. What does it mean by rate of increase in ordinate and rate of decrease in ordinate and rate of increase in abscissa? Okay, I'm just drawing a standard ellipse. Okay, so if I see one thing, decrease in ordinate and increase in abscissa. So if I go from this point to this point, right, my abscissa is increasing because x is increasing 0 to some value. Okay, and what is happening, my y is decreasing. So yeah, this is the coordinate range where my point should lie, right? X increasing this range and Y decreasing. Okay, what is happening over here? If I come from this to this point, my X is increasing because again negative to is going to 0, increasing, and my Y is also increasing. So obviously, like I'm telling you, what point is not possible. If I found the solution and I see the solution is lying in this second quadrant, then it is not possible. I have done some mistake. Okay, so yeah, that is the case. Here my X is increasing and my Y is also increasing. Now what about this? So here, right, what you can say that okay, I'm coming from this point, right? I'm coming from 0 to this negative, so x is decreasing and my Y is increasing because it is going from negative to positive. Okay, so either way you can do, you can go from here to here, but they will be of opposite signs. Here my X is increasing but my Y is decreasing, so just they are opposite signs. Okay, that way you can understand X, but I will go in the counter in the clockwise direction, right? So here my X is I will say X is decreasing and my Y is increasing. So here what is happening, X is increasing and Y is increasing also. So okay, or I can go like this in the clockwise direction. So here X is decreasing and Y is also decreasing, right? So this is also not possible, like both of them same sign, not possible. Either it can lie in first quadrant or third quadrant. We'll see that. Okay, so let's formulate the question. So they have told us the rate of change of ordinate decrease is same as the abscissa increase. So what is the rate of change of ordinate decrease? So here, right, they haven't told us anything. Basically by rate, what to mean anything, right? Rate means with respect to time. Anything when rate comes up, right, always think about with respect to time. Okay, I forgot to write this that time. Rate means with respect to time. Okay, most cases. At what rate is it increasing? Okay, at what rate is it decreasing? Okay, all those things. At what rate is it traveling? So always with respect to time they're talking about. So basically the rate of ordinate is written like this, dy upon dt, and rate of abscissa is written like this, dx upon dt. Now they are equal to each other. They are telling me that they are equal to each other. Okay, same rate, they are same, but it is increasing and another one is decreasing. Okay, or this is decreasing and another one is increasing. So obviously same rate but of opposite signs. Okay, opposite signs. Magnitude will be same but of opposite signs. Okay, so this is the case. This is the case for this. So we have to find the condition where my dy by dt is equals to minus dx upon dt. Magnitude is same but of opposite signs. So what we can do, we can we can take the derivative on both sides, right? So this will be b square is constant with respect to time, that is, this is the implicit equation. I can take the derivative 2x and the derivative of inside function is dx upon dt plus a square into y, not y square, sorry, 2y dy upon dt equals to 0, right? A square b square is a constant itself. So what is interesting fact over here is that my dy upon dt is equals to minus dx upon dy, right? So I can replace this dy upon dt with minus dx upon dy. So this will be b square 2x into dx upon dt equals to a square 2y into dx upon dt, because I have skipped one step and directly gone to the right hand side. So here in this case what is happening, my y is equals to b square upon a square into x, because dx upon dt we are assuming that obviously it is not equal, it is not 0, assuming, because I can't divide by 0, right? Okay, again my pen is not working. Dx, oh my god, what is happening? I have to buy a new pen. not equal to 0. So if dx upon dt is not equal to 0, we can do this. So next what we can do, I can replace this y, right, in this equation, because we have to know two equations. This equation I can replace my y. So here, right, what will happen, b square, oh no, b square into x square plus a square into y square. What is y square? Y square is this will be raised to the power 4, b raised to the power 4, a raised to the power 4 into x raised square equals to a square b square. Okay, so now what will happen, basically I can take the x square as common, right, take the x square as common. So this will be a square in the bottom, so this will be a square b square plus b raised to power 4 equals to a square b square, right? So basically what will be this equals to, I'm missing something, yeah, okay, I can anyways take the b square as common. So this will be left with x equals to a plus minus under root a square plus b square. What I've done, I have just taken this b square common. Okay, so this has been left with b square and this has left in a square, and this b square has been cancelled over here. Okay, so yeah, x is this and my y will be something like this. Okay, b upon, you can compute it, b upon under root a square plus b square. Okay, basically y is equals to what, y is equals to where did it go, b square by a square into x. So I will multiply b square by a square. Okay, and so this will, sorry, this is, yeah, this is y, right, into x. So yeah, a raised to power 4 is here. Oh, sorry, this a raised to power 4 is over here. Okay, yeah, this is a square only. Yeah, a square is over here, fine. Okay, a square is in the bottom also, right, a square is in the bottom also, for what. So yeah, this a square will go over here, this will be a square only. Okay, if I take the under root, and this will be b square, because this will be b square upon a square will get cancelled, and this will be b square itself, right. So the b square upon a square plus b square. Now which points will you take, so I have already established that like my both rates should be different, like opposite signs. So in the first quadrant and second quadrant, that is possible. So what I will assume is that my a and b both are positive. A and b both are positive. Anyways, that this doesn't matter because I have like whole square over here. Okay, this doesn't matter actually, I have a whole square over here. So a and b can be anything, right, negative, positive, anything. So obviously either my xy can lie in the first quadrant. Okay, first quadrant. Now these type of question can come in MSQ, right? Okay, so I'm just solving you in generalized form, but like in normal they can give you some numbers, and from there you have to solve first quadrant or third quadrant. Okay, so what is my first point? Both of them have to be positive if they are lying in the first quadrant. So my first point can be something like this. This will be a square by under root a square plus b square, comma b square by under root a square plus b square. Now only this is the possible case, and another case is when both are when x is negative and y is positive, right? That will be one of the cases. Okay, like when both are negative. Okay, sorry, yeah, here both are negative, right? X and y both are negative. Okay, so yeah, this will be the case and this will be the case. This can't be the case and this also can't be the case. Okay, so x and y both are negative, so it will be minus a square So you might say, sir, why are you stressing so much in this, right? Nobody stresses in this. But yes, GATE, what they do, when nobody stresses, they ask the question from that only. X square plus B square. Okay, so these are the possible two solutions, okay, for this question. So find the point, at what point does the ordinate decrease at the same rate? These 2 points, okay, at these 2 points. As ellipse is symmetrical, we'll have 2 points. Okay, so let's come to the next topic, that is the topic of approximations. So let's say you have to, like, this is also another very useful case of derivative as a rate of measure. Okay, so you have to approximate the value, sorry, not derivative as a rate of measure, application of derivatives. Okay, so you have to find the cubic root of 1.05. Can you find it without calculator? Without calculator, can you find it? I will say no, right? I will say no. Okay, how? So like so I will say yes, it will be difficult for you to find. How do you find? So here what we can do, we can use a very good trick, that is my f of x, I will assume that it is equals to the function itself, cube root, right, x raised to power 1 by 3. Now I will assume some very simple number for which I can find the value. So what is the, and that is close to this result, right, 1.05. What is the most simple cubic root? Cubic root of 1, right? Cubic root of 1, f of 1 equals to 1 by 1 by 3. So number, okay, choose a good number. Now what we'll do, we'll find, like, let's go a bit further from this, okay. So but actually what I'm interested in, I can easily find f of 1, that is very easy, okay. But actually what I'm interested in f of 1 plus 0.05, right, f of 1 plus 0.05. So what can happen, as I'm really close to this one, it can deviate a bit, right? It can just deviate a bit, okay. So like it will be very close to my result f of 1, okay, plus some delta y, it will be very close to 1 and plus some delta y, and this is my delta x, okay, because I am very close to 1, right? So the result will be close to this 1 only, and some delta y, it will increment or decrement. Graphically we can understand this better, but before that, right, I want to show you some first principle method that we have studied in our schools, okay. So like also we have studied in differentiability. So this is the idea of this approximation is, I'm approximating, not exactly, right, not exactly equals to 1, exactly equals to this 1.05, I will approximate. So I am really close to this 1.05. What I can do, I can take a very good point, that is x equals to 1, and that for that the under root can be easily found out. This will be 1 raised to power 1 by 3, okay. So I will find out 1, okay. Then f of 1 plus 0.05. What is f of 1 plus 0.05? So f of, like, I know already f of 1, and I just have to increment by 0.05. It will be very near, right? Very near, okay. As this graph will be continuous and all those things, it will not be deviate very far away, okay. So this will be delta y plus some delta y. f of 1 will be there and it will be delta y. Now basically what is the concept? Concept is first principle methods. So here what is this? This is the derivative, right? Differentiation, okay, at point x equals to a. If I tend my limit as h tends to 0, and this is the basic formula of differentiation, right? First principle methods, first principle formula. Now this, right, this h I can replace with delta x, okay. H has been replaced with delta x, and I will say my delta x is tending to 0, okay, tending to 0. Okay, if my delta is tending to 0, what I can do, so this is the point I am interested in, right? A plus delta x, here exactly that same format is present over here, okay. So what I am interested in is that this, right? So I have to evaluate this. I will know the differentiation. What I will do, I will cross multiply delta x on both sides plus f of a, okay, which will be equals to delta x, right? So here what is the important point over here? What is the important point over here is that you will say this is hack, right? What are you doing? You just simply find f of a plus delta x with this formula. Same thing is over here, right? Same thing is over here. This is the f of a. F of a is this, right? This f of 1 and plus delta y. So I will just swap these two to further replicate this form. Okay, this is delta y, right? Now what is the catch over here? The catch over here is, this is the catch, right? This thing is the catch. Can you guess what is the catch? Catch is this. Catch. Because my delta x never exactly equals to 0. It can't be equal to 0, right? It can't be equal to 0 because obviously I have some deviation. And obviously if it is equals to 0, I can't simply multiply delta x on both sides if it is equals to 0. It is tending to 0, but it is not equals to 0. Okay, so this is the approximation. Basically the approximation is delta x is not equal to 0. The more closer it is equals to 0, the better the approximation will be. Okay, so this is the approximation, that my delta x is not equal to 0, and this is the approximation. Okay, so this is basically the approximation, right? So we can solve using the graphical method. So what will be the graphical method? The graphical method, like you can also try to understand using the graphical method. So we are talking about the secant and the tangent, right? So here, if I am interested in the value of q, but I know the value of p, right? I'm interested in the value of q, but I know the value of p, right? So what I can do, I can take the derivative at this point. Okay, and the derivative at this point will be something like this. If I just make this more better, yeah. Okay, now this, right, I know, like if I go in this straight line, I will be at this point at a plus delta x. Okay, if I go in this straight line, okay, and I know what is f dash of a, and this difference is the approximation. Basically this difference will be the error. What do we mean by this? Let me just draw this and then I will tell you everything. So if I draw this straight line, right, if I draw this parallel line to x-axis, okay, let me use some other color. What is this angle? This angle is theta, right? This is the angle with the x-axis. This is just parallel to the x-axis, so this angle will be theta. Okay, and obviously I am moving how much distance? This is delta x, right? Delta x. And what is this? This is delta y. What is this delta y equals to? Simply how I can write it? I can write it like this, right? That if I move some delta x distance, I'll move up by delta y. Okay, so delta y upon delta x equals to what? Tan theta. And delta x equals to delta y equals to tan theta. So delta y will be equals to delta x times tan theta. Okay, tan theta. And this is basically the slope. Slope at x equals to a. Slope at x equals to a. Okay. So there is a slope at x equals to a. Now what next? What is the next point? Next point is, what is the value at this point? This is a distance, right? This is just the delta y distance. What is the value? The value is this total distance. What is this total distance? This is f of a. Okay, so the value of f of q, okay, approximation f of q I can write, just hold on a second. F of q equals to simply this, right? This distance f of a, not exactly equals to, approximately equals to f of a plus this distance delta y, that is delta x into tan theta, okay, or I can say f dash of a, tan theta is f dash of a. Okay, so like again you can observe this graphically that here, right, I'm having an error but which is very small error, right? So I'm missing, obviously I won't be able to exactly tell the value, okay, I won't be able to exactly tell the value, but this will be some value, okay, some error over here, and this will be very small. Okay, so this is very small. So this is how you understand this graphically. Okay, so yeah, let me just put this in a box. Now we were in this question, so we have to solve this question. So what is a good input? So good input is, in our case, I will first choose the function. F of x will be simply x raised to power 1 by 3. That is the most convenient function, right? Cubic root. Now I will choose a convenient point that is very near to this 1.05. So very near to this, I can choose x equals to 1 and delta x will be equals to 0.05. So what will be my x plus delta x? This will be equals to the same formula, f of x plus delta x into f dash of x. Okay, I'm interested in x equals to a, so it will be 1 plus 0.05 equals to f of 1 is 1 itself, 1 by 3 I will choose. And what is f dash of x? So f dash of x is 2 by 3. Okay, sorry, it will be minus 2 by 3. Yeah, minus 2 by 3. Okay, so this will be simply delta x 0.05 into f dash of x at that point, that is 1 by 3 into x. Now this 1 raised to power minus 2 by 3. So this will be simply equals to, I can say, f of 1.05 is simply equals to 1 plus 0.05 divided by 3. What is it? It is 0.0167. Okay, because if you multiply this with 3, you will get back your 5, right? Yeah, so this will be 1.0167. okay, so let's see how good approximation this is. So here this part becomes simpler, okay, computing this part, because I had only one over here. I have only one over here, right? So this is 1.067. Let me find out from calculator what is under root of, like not under root, cubic root of 0.05. So 1.05, and I will take it to the power of, is it 0? No, 1 divided by 3. It is 1.0164. So actual value 1.0164. So these are very close, right? Very close to each other. So that is the power of this. Without even using the calculator, I can simply compute the derivative, but we had to go through more steps, right? That is a disadvantage of this, but the power is also very good, right? So yeah, this is how you solve these type of question of approximations. Okay, so here I have few notes about error calculation. So simply you just go through this note. Okay, this, right, this is the absolute error. So the absolute error is this minus this, exactly this actual minus the calculated value, actual so practical value minus actual, whatever you do, they will define, they'll give you the error. Okay, practical minus actual error. So practical is this 1.0167 and actual is this. So you go to the labs and all those things, so you measure the practical value and the actual value from theoretical results, right? So yeah, this is the absolute error, or they may say also the deviation from the actual value. Okay, next is the relative error. What is the relative error? Relative error is basically with respect to the error, when not with respect to the error, with respect to the quantity what we are measuring. Okay, so this is very important, and most cases they will give you this. So this is known as the with respect to the quantity that we measure. With respect to quantity that we measure. Okay, so basically what we do, simply we just divide by the actual value. We have already done this. Okay, you already done this, and we find the percentage error at the end. We just multiply 100% with the relative error, and that is the percentage error. Okay, these things are very basic. Okay, so let's just do a question quickly and we'll understand the concept. We have to find the relation between the relative errors of the volume and radius of a sphere. Between the relative errors of a volume and radius of a sphere. So what are they asking us? So here, right, it is delta q upon q. We'll understand this as delta v upon v. Okay, delta v upon v. So what you do? So what are they asking us to find? Delta v upon v and delta r upon r. So this obviously you have to write first, right? What are they asking us to find? Okay, so I mean, this delta v and delta q are this only when they are very small. So what is my volume? Okay, so if you have to find the relationship between this rate of change, obviously you have to find the you have to write the equation, the relation between the volume and the radius of the sphere. So my v is equals to 4/3 pi r cube. Okay, 4/3 pi r cube. And obviously I can again differentiate with respect to delta v upon delta t. Okay, equals to 4/3 into 3 pi r square into delta r by delta t. So like generally we don't write this step, we cancel delta t, right? We cancel delta t and we directly write here, we directly write that my delta v equals to 4 pi r square delta v, and we ignore this step. I don't know why, because they don't want to write this cancellation of delta t, right? They don't want to write this. So what is this delta v? This delta v is absolute error, right? Absolute error in volume. Okay, this is delta r, not delta. This delta r, right? Delta r is also absolute error in radius. Okay, so but what have they asked us to find? They have asked us to find this, right? So I have to divide by volume. Okay, and here also if I divide by volume, I will just replace this v with r. So if I divide by volume, delta v upon v on both sides, this will still remain pi r square dr. Now, right, what I will smartly do, I'll replace v with this equation. So this will be 4 pi upon 3 into r cube. So what does this become? Delta v upon v equals to this, right? This is 4 pi gets cancelled, r square r gets cancelled, 3 will go above, 3 delta r upon r. Okay, so this will be the relation between the two quantities. Okay, relative error of two quantities. If one has error as this 1 unit, so delta r will have lower error. Or you can say if delta r, like radius, has relative error of 1 unit, then the relative error of volume will be 3 times that of radius. Okay, very important. So relative error of volume will be greater because it is expanding in all directions. Radius is only expanding in one direction, so its relative error will be smaller. Volume will have higher relative error. It is expanding in all directions, so that error gets multiplied, right? So that is the case. We have solved this question. So like what other method you can do? You can take this method too. Whenever you have to find the relative error, you can use this method. How to use this method? Take log and differentiate later. Why? Because if I take log and then differentiate, that term, right, the term will come in the denominator, and exactly that is how my format of relative error is. So here what we'll do, we'll take log on both sides. So what relation I have volume equals to 4 by 3 of pi r cube, right, pi r cube. If I take the log of both sides, log, I can take ln of v equals to this, what I can do, this ln of 4 by 3 pi r cube. Now what I can do, I can put the constants in one side and the variable in the other side, because this is constant, right, and I can like replace this one single log into two logs, as this is multiplication, right, log a plus log a b, log a times b is equals to log a plus log b. So this ln v will be equals to ln 4 by 3 pi plus ln r cube. Okay, so now what I can do, I can differentiate on both sides. If I differentiate, so this, if I differentiate, this will be 1 by v into dv upon dt, and differentiation of this is a constant number. Log of 4 pi by 3 is a constant number, so this will be 0, plus again differentiation of this will be 1 by r cube into r square into dr by, sorry, this will be 3r square. First I'm using chain rule. First the outside function, that is log, then the inside function, that is r cube, then the inside again, that is the r. So dr upon dt. Okay, so what will happen over here, basically this will get cancelled, this will be dt, I can cancel, right, dv upon v will be equals to this r square, r cube will get cancelled, I will be remained with 1 r, so this will be 3 dr upon r, right. We are getting the same relation that we earlier got. So this is the equation. Okay, so obviously we are cancelling out dt because we don't care about that. Same, we are talking about the same change, right, same change in time, so we're not talking about that. Okay, so yeah, this is how you can solve this types of question. So let's do another question. What are they telling us? The radius of a equation was radius of a sphere was measured and found to be 21 centimeter with a possible error in measurement of at most 0.05 centimeter. So here, right, whenever there are units, so this has units, I will say this has units, and these two, right, these two are unitless. So these two are unitless and this has units. Okay, so yeah, so whenever they are giving you error as a unit, so that means they are talking about the absolute error. So they are talking about this delta r equals to 0.05 centimeter when my radius was measured to be, r was measured to be 21 centimeter. Okay, with a possible error in measurement at most. What is the maximum error in using this value of the radius to compute the volume of the sphere? So how to solve this? We just solve this, right? We just solve the relationship between the relative error of volume and radius. So we'll use this here. So here they have given us this del r, they have given us this r. Okay, and I have to find the maximum error that can be happening in volume. So basically this, right, what can be the error in volume? This is the dv. Okay, so also they should have mentioned the units. Okay, in cubic centimeter. So here, what will my volume at this particular radius? What will my volume? Volume will be 4 by 3 pi r cube, which is 21 cube. Okay, I'm just equating, I'm not solving it right now. So here I can use this volume here, right? So what will happen? So dv upon 4 pi, okay, I have written this pi twice. Four pi by 3 into 21 cube equals to 3 into dr by r. What is r? Is 21. Okay, so r is 21 and dr is what? Dr is simply 0.05. so my dv, okay, or I can say delta v will be equals to this, can go up there, 3 will get cancelled. This will be 4 pi into 21 square, because 121 is in the denominator, and it will be multiplied into by 0.05. okay, so this is the case. So if I compute this, right, if I compute this, what will I get? Let me compute this actually. 21 square into 4 into pi into 0.05. yeah, 277 I'm getting, right? So this is 277. Now don't forget the units. This is cubic centimeter. Okay, because this is the actual deviation in volume, and this will be the maximum deviation in volume. It can't go above that. If the radius has this much deviation, then the volume will have this much deviation. We have already found out the relation from the previous question. So I have you understood this question. Okay, we are doing nothing. Okay, they have given us the absolute deviation from radius, but to find the absolute deviation from volume, you just have to write the equation which relates this delta r and v, right? You have to write that equation. After you write that equation, you just have to understand what you have to find. You have to find, like, del r is given, r is given, you have to find v. What is v? V is 4 by 3 pi r cube. So you find out 4 by 3 pi r cube, you find out v, and then you put it in this equation, and from there you will be able to find dv. So any gate question, right, you just have to understand what equation is being used. Obviously, fundamentally, right, don't just mug up equations. Those are fundamental equations, okay, and from there also you may sometimes also have to derive your equations, okay. That is very important. So this is the end of this lecture, okay, basically, and in the next lecture we'll start from equation of tangent at a point and more about tangents, okay, and more application of derivatives. So I will see you in the next lecture.